Hello everyone and welcome to the Operating Systems lecture. Today we continue with Chapter 1 on computer system hardware. We will look at the different types of memory that are used in a computer system. The design constraints of a computer's memory can be summed up by three categories: capacity, speed, and the price. The capacity is related to the question of how much can a certain memory component store. The speed refers to the question of how fast can the processor access a certain type of memory in terms of loading data or storing data. And the price refers to the cost per bit of a type of memory. It is not possible to manufacture memory that is top in all categories, meaning having a high capacity and speed and a low price at the same time. But there are some generally desirable properties that a memory component in a computer system should fulfill that can be actually achieved. For instance, it makes sense to have memory components that can keep up in speed with the processor. If we would have a system with a very fast processor, but only memory with a slow access time, then the memory would become the bottleneck of the system. It would slow down the processor, because now the processor would have to wait longer to load instructions from memory. Another design matter is that for a system to be practical and economic, the cost of memory must be reasonable in relationship to the other hardware components in the system. It doesn't make sense to combine high-end and low-end components in one computer system, so the quality of the used components shall be similar. On the previous slide, we already mentioned that no perfect memory solution exists. We cannot build memory that is great in all characteristics like capacity, access time, and cost. The following trade-offs hold for the key characteristics of memory. The faster the access time, the greater is the cost per bit. The greater the capacity, the smaller is the cost per bit. And the greater the capacity, the slower is the access time. So if one wants to design a computer system, these trade-offs need to be taken into account. Later we will see that the key concept for great performance in a system is to use multiple levels of different memory types, so-called caches. An effective hardware memory design makes use of a memory hierarchy. Here we can see a pyramid illustration of such a hierarchy. At the top of the pyramid we have the registers. That are the memory units that are integrated in the processor. Then we have the cache. The cache is the memory layer between the registers and the main memory, and the cache will be also the major topic of the lecture today. In the hierarchy, the cache is followed by the main memory, and the registers, together with the cache and the main memory, form the inboard memory components of a system. Then we have a number of outboard memory components, such as hard disk, CD, DVD, and Blu-ray. And at the bottom of the pyramid, we have offline memory components. An example of an offline component is magnetic tape. A register can typically only store a single instruction, which consists of a small number of bits. So now, after we have seen an overview of the components that we can find in the memory hierarchy, we will now discuss the relationship between the components. If we are going down in the hierarchy, then we have that the costs per bit decrease. That means the registers of the processor are the most costly type of memory, whereas magnetic tape has a very low cost per bit. Moreover, if we are going down in the hierarchy, then the capacity of the components increases. In contrast, hard drives have a much higher capacity. Modern hard drives can even store terabytes of data. Another property of the memory hierarchy is that if we are going down, then the access time increases. So the registers are faster than the cache is faster than the main memory, and the main memory is faster than the hard drive when it comes to the access time. The three properties of the memory hierarchy that we have discussed so far are facts. There's a fourth property that is not a fact but a design matter. In a properly designed computer system, if we are going down in the hierarchy, then there should be a decreasing frequency of access to the memory by the processor. So it is the job of the system designer to ensure that the processor will mostly access the registers, followed by the cache, followed by the main memory. In particular, it should be avoided if possible that the processor accesses the hard drive or even slower memory devices. So in order to have a good system performance, the processor should access the faster types of memory more often than the slower types. In order to illustrate the performance effect, we will look at an example where we assume that we have two different types of memory that we call here level 1 and level 2. Level 1 memory has a capacity of 1000 bytes and it has an access time of 0.1 microseconds. So we have a small but fast memory component that may correspond to a cache in a computer system. Then level 2 has a capacity of 100,000 bytes and it has an access time of 1 microsecond. So we also have a slower type of memory with a bigger capacity. This might correspond to the main memory of a computer system. Now we assume that the computer in this example behaves as follows. If some data that is required by the processor can be found in level 1 memory, then the processor will directly access it. If the required data is not in level 1 but in level 2 memory, then it will be first transferred to level 1 and then accessed by the processor. For this example scenario with the two levels of memory, we can determine the average access time of the computer system. The average access time is a function of the so-called hit ratio. And this hit ratio is a percentage of memory accesses that can be found in the faster level 1 memory. So in the worst case, if all memory accesses by the processor could be only found in the slower level 2 memory, then we would have a hit ratio of 0%. In the diagram, we can see that the average access time corresponding to a hit ratio of 0% is 0.1 plus 1 microseconds. Because in this worst case, each piece of data that the processor needs will be transferred from level 2 to level 1 memory first, which takes 1 microsecond, and then it will be accessed by the processor, which takes additionally 0.1 microseconds. And in the best case, where we have a hit ratio of 100%, we can see that the corresponding average access time would be 0.1 microseconds. Because here we have that each piece of data that the processor needs can be immediately accessed from the fast level 1 memory. Now let us assume that the hit ratio is 95%. In the red box you can see how the corresponding average access time can be computed. In 95% of all memory access cases, we have the fast access that takes 0.1 microseconds. And in 5% of the cases, we have the slow access that takes 1.1 microseconds. 1 microsecond for copying data from level 2 to level 1, and 0.1 microseconds for accessing the copied data. Now if we solve the sum, then we get 0.15 microseconds as the average access time. The average access time is very close to the access time of the faster memory. So the strategy of using two memory levels works in principle for a good system performance. The previous example has shown that a high hit ratio gives us a low average access time. The question that remains is, how do we achieve a high hit ratio? And here the so-called principle of locality helps. It can be typically observed that if a computer program is executed, the memory accesses by the processor tend to cluster. For instance, if you think of a computer program with a loop, then the instructions in the loop body will be executed again and again, which means they form a cluster. Or as a second example, if a computer program iterates over an array, then typically multiple elements of the array will be accessed. An array is typically stored as a block of data in the memory. So this block of data will also form a cluster of frequent access. So such a cluster of data or instructions that has been currently used by the processor will also be most likely used by the processor again in the near future. Therefore, those clusters are good candidates to be moved to the fast cache memory in the system. What we can see here in this illustration is how the interaction between the processor, the cache, and the main memory works. The access to the cache is fast, but the cache has a very limited capacity. On the other hand, the access to the main memory is slow, but here we have a much larger capacity. Now let us consider the following example. The processor wants to access the word that is marked in red here. So that might be either an instruction or a piece of data. At first, the processor will check the cache, if there exists a copy of the memory block that contains the red word. And we see that this is indeed the case, so the processor can load the red word directly from the cache, which will happen very fast. And due to the principle of locality, it is also highly likely that other words from the same memory block will be accessed by the processor in the near future. Now let us discuss a second example. At some point in the future, the processor may want to load the word that is marked in blue here. We see that the blue word cannot be found in the cache. So what will happen now is that the memory block that contains the blue word will be copied into the cache. The challenge that we have here is that the cache is much smaller than the main memory. So a block in the cache may have to be removed in order to make space for the new block to be copied from the main memory. So that may be the memory block containing the red word, which gets now replaced in the cache by the block containing the blue word. Transferring this block from the main memory to the cache will be generally slow, but due to the principle of locality, we can expect that the processor will, at the near future, also access other words from the same block, so in the long term we will profit from moving the block from the main memory to the cache. What we have illustrated here is the simplest cache scenario, where we have only a single cache located between the processor and the main memory. But in modern computer systems, we will find multiple levels of caches, each with different capacity and speed, and they will exchange memory blocks based on the same principle that we have illustrated here. Managing a cache requires some technical organization in order to ensure that each memory block can be always uniquely identified in the cache. If we look at the right, then we can see the main memory that consists of 2 to the power of n addressable locations, where each location can hold a word. In order to use a cache, the main memory has to be divided into blocks, where each block consists of the same number of words. For instance, we may define the block size as 64 words, and our main memory may consist of 1,000 of those blocks. Now on the right, we have our cache memory that consists of a number of slots, where each slot can hold a block. The number of cache slots is typically much smaller than the number of blocks in the main memory. So we may assume, for instance, that we have 10 slots in our cache. Since we already said that we assumed that we have 1,000 blocks in the main memory, only a small portion of these blocks can be held in the cache at the same time. Now, if the processor wants to access a word that is not contained in the cache, then the block that contains the word needs to be copied from the main memory to a cache slot. Either there will be an empty cache slot that can be used for that, or the content of an occupied cache slot needs to be replaced. If a new block is added to the cache, then a binary tag is added to the block such that it can be uniquely identified. Here we look at a simple example for tagging. We assume that the white block in the memory shall be copied to the cache. We can see that the addresses of the words in the cache block all start with the same prefix, which is 01. So the common prefix of the words in a block can be used as a unique tag when the block will be copied to the cache. Now, if the processor wants to access a word that is stored at a memory address that starts with 01, then it can see that the corresponding block is already contained in the cache, and it can be immediately accessed from there. The following diagram summarizes what happens if the processor tries to read a word that is either contained in the main memory only or also in the cache. At the start, we have that the processor wants to read from the memory address RA. Now it will identify to which memory block the address belongs to, and it will determine the tag of the memory block. If the tag can be found in the cache, then the corresponding memory block is also contained in the cache. In this case, a fast access is possible. The word at memory address RA can be fetched from the cache and delivered to the CPU, and we are done. Now we consider the second case, where the block corresponding to the memory address RA cannot be found in the cache. The processor accesses the main memory, and it looks for the block that contains the address RA. Now a slot in the cache will be allocated in order to store this memory block. This may be either an empty cache slot or an occupied slot where the current content gets replaced. The memory block gets loaded into the cache slot, and the word at address RA gets delivered to the processor. In this case, we only have a slow memory access, but we can expect faster memory access in the near future due to the principle of locality. It is very likely that the processor will access words in the near future that are part of the block that we have copied from the main memory to the cache. Now, after we have discussed the motivation behind a cache and its general functioning, we will now have a look at the cache design questions that needs to be considered in order to ensure the efficiency of a cache. Cache design questions can be categorized into the following 6 groups. We have the size of the cache, and that is always a matter of cost. The corresponding question is, how much cache in a computer system is affordable? Then we have the block size. The question is, should we rather use big blocks to be copied to the cache or smaller blocks? Then we have the mapping function, which deals with the question where in the cache a new block shall be placed. The mapping function is closely related to the replacement algorithm. If the cache is already full, then we have to decide which current cache block shall be replaced by a new block. The write policy deals with the matter of keeping the copies in the cache and the original data in the main memory consistent. And the final design question is, how many levels of cache shall be used? In our simple example, we had only one cache, but in most modern computer systems, you will find at least 3 levels of caches. We will now look at some of those design questions in a bit more detail. We start with the cache size and the block size. When we looked at the 2-level cache example, we could already see that even small caches can have a significant impact on the performance of a computer system. Another size matter is the block size, which is the size of the data unit that is exchanged between the cache and the main memory. If we choose very large blocks, then we will most likely profit from the principle of locality, because it's highly likely that the processor will also access data in the near future that surrounds the currently accessed word. So if we choose a large block size, then a lot of this data will be contained in the same block that contains the currently accessed word. And since the block has been moved to the cache, we get fast access to each element of the block. However, if we choose the block size too large, then this will involve performance disadvantages. If the blocks are very large, then it becomes more likely that for moving a new block to the cache, an old block has to be removed from the cache. Now, if we remove a lot of blocks from the cache, then it becomes also more likely that we remove a block that is needed by the processor in the near future. So if the block size is chosen too big, then that may also involve a decrease of the performance. The next design question we are looking at is the mapping function. When a new block of data has to be moved to the cache, then the mapping function will determine which cache location will be used for that. There are two major constraints that affect the design of the mapping function. The first one is when a new block has to be moved to the cache, then an old block may need to be moved out of the cache. And a good mapping function should minimize the probability that we remove a block from the cache that will be needed by the processor in the near future. The second constraint is the more flexible the mapping function, the more complex becomes the search in the cache. That means if the mapping function takes too many parameters into account, then computing the result of the mapping will take some extra time, and that will also lead to a decrease of the system performance. We continue with the next design question, which is the replacement algorithm. If the cache is completely full, then the replacement algorithm chooses the block to be moved out of the cache in order to make space for a new block. Ideally, we should replace the block in the cache that will be not needed for the longest time in the near future. Of course, since we cannot look into the future of a computation, it's impossible to identify such a block. But we can use an effective strategy that will make good replacement decisions in most of the cases. And this is the least recently used strategy. It replaces the block that has been in the cache for the longest time with no access by the processor to it. If a block hasn't been accessed by the processor in the near past, then it's also highly unlikely that the processor will access the block in the near future. And because of that, the least recently used approach typically works very well. If the system shall follow this strategy, then the least recently block must be identified, which requires some extra computations. And the final design question we are looking at is the write policy. The write policy dictates when an updated cache block is written back to the main memory. In order to illustrate why a write policy is needed, we look at our previous example again. We have a single cache, and as you can see, the cache contains a copy of one of the blocks of the main memory. So it is likely that the processor will access some of the words that are contained in this block. The processor can now directly access the content of the block via the cache. And an access may involve an update of the words in the block. For instance, the processor may modify the word that is indicated in red here. Here, the updated word is now indicated in blue. However, the update has only happened in the cache so far. In the main memory, the update has not been applied yet. So now we have an inconsistency. The original block in the main memory is not consistent with the copy in the cache anymore. And that may cause a problem if we would have multiple processors in the system. For instance, a second processor that has its own cache may now access the main memory and receives outdated data. So the write policy must ensure that updated blocks in the cache are frequently written back to the main memory in order to establish consistency again. One extreme writing policy would be to update the main memory each time when a cache block gets updated. But that would be very inefficient because it involves a lot of access to the slow main memory. The other extreme would be to do writebacks only when an updated block gets moved out of the cache. But then we would get a lot of inconsistency between the cache and the main memory, which can become a problem in a multiprocessor system, as we already outlined. And multiprocessor systems is a topic that we will look at next. The first type of multiprocessor systems that we are looking at are symmetric multiprocessors, which are standalone computer systems with the following characteristics. There are two or more processors in the system with a similar capability in terms of the operations that the processors can perform. The processors have a shared main memory and they are interconnected via a system bus. And that also implies that the access time of the processors to the memory is approximately the same. The next characteristic is that the processors share the access to all the input and output devices in the system. Moreover, all processors can perform the same functions. That is why we call them symmetric processors. And the final point is that the multiprocessor system is controlled by a single operating system that allows for communication between the processors via shared memory. In contrast to single processor systems, symmetric multiprocessor systems have a number of advantages. With multiprocessors, we typically get a better system performance because now work can also be done in parallel. For instance, if there's a number of instructions to be executed that are independent of each other, then they don't have to be executed in a sequential manner, but they can be executed in parallel by the processors of the system. Another advantage is the better system availability. If one processor in the system fails due to a technical defect, then the other processors can be used as a backup. That means the entire system will not fail, it can continue running at a slightly lower performance. Incremental growth is another advantage because each additional processor enhances the performance and also the availability of the system. Finally, multiprocessor systems also have a better scaling. Computer vendors can offer a range of products with different price and performance characteristics based on the number of processors in the system. It has to be noted that all of these points are potential advantages and not necessarily guaranteed advantages. In the end, it is the operating system that has to ensure that the user can profit from a better performance, availability, and so on in a symmetric multiprocessor system. In this figure, we can see how the components of a symmetric multiprocessor system are organized. We have multiple processors, and each processor has two levels of dedicated cache memory. Via the system bus, the processors are connected to the shared main memory. Since we have local caches and a shared main memory, it is important to have a good writing policy that ensures that the contents of the caches and the main memory is consistent. Not only the main memory is shared, but also the access to input and output modules, such as keyboards, screens, and so on. As a small exercise for you, you can consider the mathematical expression at the bottom of the slide. If we would have only one processor, how many instruction cycles would we need to compute this solution? And with a multiprocessor system, which instructions that are needed here could be executed in parallel? A second type of a multiprocessor system that we want to consider here is the multi-core computer. In contrast to a symmetric multiprocessor system, where each processor comes on a separate chip, in a multi-core computer we have two or more processors, which are also called cores, on a single chip. And here each core consists of all the components of an independent processor, such as registers, execution units, and caches. Besides the integrated local caches in each core, there are also shared caches in a multi-core computer. The communication between the cores is typically very fast because everything is wired on the same chip. In a multi-core computer, the main memory and the input and output adapters are still on separate chips. Memory and PCI controllers enable the cores to communicate with those separate chips. Here we have an example of a multi-core chip, which is the Intel Core i7 that you might have in your laptop or desktop computer. The figure at the top illustrates the layout of the chip. We have the cores, they are numbered from 0 to 7, and each core comes with two levels of local caches, L1 and L2. You can see that the local caches have quite a small capacity. For instance, the level 2 cache has a capacity of 256 kilobyte. The local cache is followed by a shared cache at level 3, and for the communication with external chips, we have the controllers. The DDR controller connects the chip with the main memory, and the PCI controller connects the chip with input and output devices. The photo at the bottom shows an actual Intel i7 chip, and it gives you an idea how small the chip is. We are now finished with the lectures on Chapter 1, Computer System Hardware, and here's a summary of the topics that we considered. We looked at the basic hardware elements that can be found in a computer system and at the evolution of the microprocessor. Moreover, we have seen how the processor executes instructions that are stored in the main memory. We have seen interrupts, which is a concept by which input and output modules can pause the execution of a user program, which typically leads to a better utilization of the processor. In today's lecture, we introduced the memory hierarchy, and we identified the cache as the memory layer between the registers and the main memory of a computer. Using a well-designed cache can lead to a much faster access to data and instructions by the processor. And finally, we looked at multiprocessor systems and their advantages. The next lecture will start with Chapter 2, which is on operating systems overview.